I'm going to pause here also because we can now talk a little bit about an object on a ramp, and I think this is worth thinking about. So if I have an object on a ramp, I can draw a free body diagram for this, and we'll do more of this later. But we know if this is on the ramp, it's probably going to have a normal force, right? Because it's touching a surface. And we know that there's also a force of gravity on it as well, right? Because it has, if this block has some mass. So the force of gravity is always straight down, and our normal force is always perpendicular away from the surface, which is going to be up like that. If we do have friction, it is going to be parallel to this surface, but what direction it is depends on context. So I'm going to put friction, question mark, friction, question mark. And the answer is it could have both depending on what's happening in this problem. We need to say one more thing about friction, and that is the direction of friction always opposes the motion of the object on the surface. So in other words, if our object is sliding down the ramp in the case of kinetic friction, or trying to slide down the ramp in the case of static friction, our force of friction is going to oppose that. Our force of friction is going to be up. If our object is trying to be pushed up the ramp, right, we could have somebody, pushing this block up the ramp, whatever. In that case, the force of friction would actually be opposing them pushing it up, so the force of friction would be pushing the block down the ramp. So either of these apply. We have to kind of figure this out from the context in the problem. So, which way up or down the hill it goes, well, that's going to depend. All right. On to the next kind of force. So the next kind of force is tension. So tension is the force we have from things like string or ropes or chains or cables, all of these things that can pull on something but cannot push on something, right? If I have a rope tied to a block, I can pull it across the floor, but I cannot use that rope to push it across the floor. So tension is the force of string, rope, cable, / everything like that you can think of, pulling on an object. So the direction of the tension has to be in the direction of that string. So from now on, I will just probably call all of these things collectively string or rope. I'm not going to say this or this or this every time. So the tension has to be in the direction, or I should actually be more careful. It should be pulling in direction of the string. So if I have a block with a rope tied around it, the only direction the force on this block from that rope can be is pulling in the same direction that the rope is. If I'm given a picture instead where this rope is not horizontal, it is up at an angle, the force still has to be in the direction of the rope, so the force has to be up like that. So this is, if we have a picture, this is easy to figure out. In some problems, we will be told how big the tension is. In some problems, we are not. And in that case, we kind of have to figure out how big it is from context. So the tension, so it kind of in keeping with normal force and friction, our tension is as big as it needs to be to keep the rope the same length. So we're assuming that our ropes do not stretch. That also means, if I have a block here with a rope tied to it and I pull the rope 1 meter in that direction, this rope is not changing length, and so the block also must move the same distance, 1 meter in that direction. And we'll see examples of that later on. Tension can be a complicated thing to deal with in some problems. We're going to make some assumptions in this class to keep it simple. So we're going to assume our string is massless. So a more complicated treatment could assume that the rope has some mass, and that is going to change things. We're going to assume all of our ropes and strings have no mass, so we don't have to worry about F equals ma for the ropes or things like that. They are frictionless, so while our block on the table might feel friction with the table, the rope that we're pulling it with does not itself feel any additional friction. And this also means if we have a rope that is going around a pulley, so we could have a wheel, a wheel that turns and changes the direction of our rope, right? We have some block here and we're holding it up by, holding on to the rope there. We're going to assume that this pulley is frictionless also. And the result of all of these assumptions give us one important fact about tension that we are going to use, and that is for a particular continuous piece of rope, the tension is the same everywhere. Meaning that if we know how hard the person is pulling here, whatever that tension is in the rope, that is the same tension that is pulling up on the block over here. So this tension is the same at this point, and this point, and this point, and this point. That doesn't have to be true if we have ropes that have mass or we have friction in the pulleys or something. So that's why we're making these simplifying assumptions. So we can always assume in this class that the tension is the same at every point in the rope. So in other words, at both ends of the rope, it's pulling with the same force. All right, that's tension. And again, we don't have an equation for how big tension is. That is something that we have to figure out from context. And there will always be, if we need to know the tension, there will always be enough other information for us to figure it out. Okay, our last kind of force. Springs. Okay, so I did not bring a spring for a demo, but a spring, like a coil of wire that is stretchy, right? So I can take both ends of this spring and I can pull on it and make it bigger, right? So when I pull on the spring, I make it bigger. And when I do this, it is pulling back on me. So this force is like me pulling on spring, and the spring is pulling back on me. This is Newton's third law, right? So the spring always wants to oppose the force you're exerting on it. Now, we can have springs that stretch. We can also have springs that compress. So contrast this kind of spring that we pull on that might be, this might be like a slinky or something like that. Contrast that with something like a bed spring or, a spring in a mattress where it starts out with some height to it, in the case of a mattress spring, and you compress it, it gets shorter, you push down on it, and it pushes up on you. So springs work both ways. We can stretch or compress them. And when we do that, they exert a force the opposite way. If you compress them, like push down on it, it pushes the force up on you. If you stretch it, up is pulling back down on you. So springs have an equilibrium length, meaning if you don't exert any forces on a spring, that spring has a length that it will just stay at naturally. So this equilibrium length is when the force on it is equal to 0. So if you, so you can take that spring and stretch it or compress it. The equation for this is the following. Our spring force, F sub S, so this is equal to, now I'm gonna be careful here. So this is the magnitude of the spring force. This is telling us how big the force is. This is equal to K times the magnitude of delta X. This is the change in the equilibrium, or I should say change from the equilibrium length. This K is the spring constant. So this is a property of a particular spring, and it tells us how stiff or how soft the spring is. So big values of the spring constant are going to be stiff springs that are hard to compress or stretch. Small values of the spring constant are softer springs that are easy to stretch and compress. Spring constants are, these are actually used in real life. If you are a mechanical engineer buying springs, you can go to a spring catalog and say, oh, I want a spring with a spring constant of 2 newtons per meter, and it has to be this long. And, spring constant is something that people care about in real life. So yeah, our units of the spring constant are newtons per meter. We can see that here, if we plug in newtons per meter and multiply it by meters, we get newtons back. So that's good. Spring constant values that we encounter on a day-to-day basis are kind of, the ones we use in the lab, they're kind of like springs you can easily stretch with your hands. They're, a few newtons per meter or something like that. Springs in car suspensions might be thousands of newtons per meter. And there are, tiny springs in, I don't know, your watch or something like that that have small values of the spring constant, I'm sure. All right. So this told me the size of this force. This equation is sometimes also written Fs equals a minus K delta X. And this is to try to include this information about this direction. So in other words, this is trying to kind of think of the force and delta X as vector components, or at least as something with direction. So rather than the magnitude of the force, they're saying, okay, well, let's say I have this spring, here's a wall, right? I have a spring against that wall, F equals 0. And let's say I stretch that spring out. So I have changed its equilibrium length by some amount delta X. I have stretched it bigger by this amount delta X. Well, the force that the spring is pulling on you with is going to be back to the left, and it's going to be equal to K times delta X, and it is in the negative direction, so that's why this minus sign is here. So you see both of these. Really, you can use, the safest thing to do is to use either one and then think about what direction the force is in and adjust your plus or minus sign accordingly. That is what I do. That is what I recommend. But the minus sign here is to remind you that the spring is kind of opposing whatever you're doing to it. All right, so these are all 4 of our different kinds of forces, and everything we're going to do in the next chapters are going to be different combinations of these forces and playing with these rules and how things apply in different circumstances.